Hello, welcome to today's video brought to you by members of Tau Beta Pi. Today's topic is Norton's theorem. Norton's theorem states that a linear two-terminal circuit can be replaced by an equivalent circuit consisting of a current source, I Norton, in parallel with a resistor R Norton, where I Norton is the short circuit current through the terminals and Rn is the input or equivalent resistance at the terminals when the independent sources are turned off. So what does that mean exactly? Whenever we have a Norton equivalent circuit, we think of that equivalent circuit as this kind of box where it's an abstracted circuit. We don't really care how complex the circuit is. All we care about is the characteristics that the circuit has. And in the Norton equivalent circuit case, we understand it to be a current source driving a parallel resistor and whatever load resistance we may choose to hook up to that circuit. So whenever we're finding our Norton circuit, we choose to find the current that would go through the AB terminals if A to B was a short or a wire. And then when we're finding the Norton resistance, we would be looking into the AB terminals with our independent sources off and determining what the equivalent resistance would be. In the case of a voltage source, we choose to short the voltage source. And in the case of a current source, we create it as an open and then find the equivalent resistance that remains. So let's go ahead and do a practice problem. So let's say, for example, we have this circuit. In order to find the Norton current, we would choose to find the current if there was a short between A and B, if we place a wire between the AB terminals. So one way we can accomplish that is by doing a source transformation on the 15-volt current voltage source and the 3 ohm resistor, and that would create a circuit that looks like this, where we have a 5 amp current feeding into our circuit with the 3 ohms now in parallel, and the other parts of our circuit still intact from that source transformation. So our 4 amp current source, our other 3 ohm resistor, our 6 ohm resistor, and then our short from A to B. And put those values into there. Now we can sum the currents flowing into this top node and further simplify it as a 9 amp current source with the 3 ohm parallel resistance, and then that other 3 ohm resistor in series with that 6 ohm resistance. All of that also being parallel to that short from A to B. Now, if we were to find the current flowing through our short circuit, we would have current going through this junction where it would split between the 3 ohm resistor and the 3 ohm resistor. And then once it got past that 3 ohm resistor on top, it would actually bypass the 6 ohm resistor and all the current would go through that short. So we end up with a current divider. So we can take our source current, multiply it by our resistance over the sum of the resistances. And so we know that our Norton current, or the current going through our short circuit, is 4.5 amps. Then we can look at our circuit again, this time choosing to open our current source and look at the impedance that we would see from terminals A and B if we hooked up a multimeter. So this causes a circuit that can be simplified to our 6 ohm resistor, and then that 3 ohm resistor and the other 3 ohm resistor can be collapsed in series to be another 6 ohm resistor. So we have two 6 ohm resistors in parallel. So this means that our Norton resistance is equal to 3 ohms, because we would have 6 times 6 over 6 plus 6. This comes down to 36 over 12, which is 3 ohms. So that's where that value comes from. So now we know that our Norton current is the 4.5 amps, and the Norton resistance is the 3 ohms. And that matches our answer at the top. Perfect. So now, whenever we're solving our circuits and simplifying them to our Norton equivalent, we can also relate them back to our Thevenin equivalent circuits, because the Thevenin and Norton equivalents are also simply source transformations themselves. So our Thevenin resistance is equal to our Norton resistance, which is also equal to our open circuit voltage divided by our short circuit current. And so these relationships help us to go back and forth between a Thevenin and Norton circuit. And that's all for this video today. Thanks for watching.